All right, thank you. I'm Lei Zhang, a research scientist at ByteDance. I work on reliability and performance analysis for our AI infrastructure over RDMA. Today, I'm going to talk about our recent work on improving the large language model training reliability at runtime. Today's large language model training jobs span tens of thousands of GPUs and often runs for days or even weeks. At this scale, the system becomes extremely sensitive. Even small glitches can have outsized impact. Training efficiency is fragile. A single fault, whether on hardware, software, or networking related, can derail the entire job or silently waste compute. At this time, reliability is both more difficult and more essential than ever. Issues are inevitable, but our observability is often too coarse or delayed to respond quickly. This creates a growing need for fast, automated systems that can detect and diagnose problems as they happen, not just after the fact. Let's now look at existing observability across model training. We already have a wide range of signals, different hardware metrics, system counters, logs, and profiling traces. But despite this wealth of data, observability in practice is still limited. Metrics can vary across workloads and hardware, and different faults manifest differently on workloads. Failures often propagate indirectly. A root cause on one machine might appear as symptoms somewhere else. Logs and traces are often coarse, missing necessary information to reveal the actual root cause. And when issues do happen, manual diagnosis is slow, often requiring deep expertise and coordination across multiple teams. All of this points to the need for finer-grained observability. In this talk, I'm going to introduce our solutions to leverage different fine-grained observabilities to improve reliability in our daily large language model training systems. First, I'll talk about how we leverage metrics for efficient and accurate debugging. Even though we have many collected metrics, using them may not be trivial. Let's take a look at an example of PCIe downgrading and justify how such process is tricky. When the PCIe downgrading issue occurs at a receiver NIC, it causes the NIC to reduce its data transmission rate. As a result, the NIC buffer quickly filled up, triggering the NIC to send more PFC signals to the transmitter side. Before the transmitter could adjust and slow down its transmission, the switch buffer became overwhelmed by in-flight packets, leading to an increase in the ECN signals. Consequently, the CMP at the faulty NIC surged as well. When system developers and operators try to debug the problem, it could be confusing to figure out the real root cause among all those problematic metrics. Through our analysis, we identified several challenges in designing an accurate faulty machine detection systems. First, faults can occur across a wide range of areas, from intra-host computation to inter-host networks, and from hardware to software communication libraries. These faults are diverse in both type and proportion. When examining faults and their corresponding metrics, we observe that the same fault type can manifest as different anomalies in metrics. For instance, an SCC error might result in both high GPU or CPU utilization. On the other way, the same metric anomaly does not always point to the same fault. For example, when we see high GPU utilization, it could be either associated with GPU hardware errors, software errors, or even some network issues. Besides, defining whether a behavior is an anomaly are actually task-dependent. For example, a GPU temperature of 7 Celsius degrees is considered abnormal when the GPU clock frequency is 1350 MHz, but it's normal for tasks when GPU operates at a higher clock frequency of 1800 MHz. Additionally, we observe that metric data often contains noises caused by factors such as jitters, inaccurate sensors, timestamp misalignment, and more. These inconsistencies can mislead the detection process, making it less reliable. We have seen that it's not trivial to leverage those collected metrics to debug complex problems. Then let's think about how to utilize the correlation among those metrics. We first find that metrics across machines exhibit consistent behavior during parallel distributed training at per second observation level. When a fault occurs, such as PCIe downgrading, the PFC rate demonstrates distinctive differences compared to normal operation. This principle can be extended to other metrics, offering a potential pathway for systematically identifying the faults. To denoise the time series data, we can leverage the notion of abnormal continuity. Once a failure occurs, abnormal performance typically persists across 7 consecutive windows per second. This can be used as a reliable indicator for identifying faulty machines and rule out noises. To address task-dependent anomalies, we find that we can use individual models to represent each monitoring metric. Since the monitoring metrics are independent, these models and their respective metric data are utilized independently for both denoising and detection purposes. So with those insights, we built Minder, a fault detection system for large language model training. Minder processes metric data for each time window and generates an alert when a faulty machine is detected. The design consists of 2 key components: constructing a VAE-based per-metric model for anomaly detection and a similarity and continuity-based check to ensure accurate fault identification. To construct the per-metric models, because labeling task-dependent faults is actually challenging and may not be practical, we choose to use unsupervised learning. VAE is widely used for denoising and compressing high-dimensional features with its strong reconstruction capabilities, and is proved to be an effective option in Minder. In Minder, we deploy LSTM as both encoder and decoder, given our data consists of temporal time series. LSTM is also shown suitable in our cases, as it considers both forward and backward information, enabling it to extract the complete correspondence information from the data. With the constructed per-metric models, Minder achieves runtime detection that applies the concept of machine-level similarity and continuity as from our insights. For each time window, Minder first pre-processes the raw data and uses the pre-trained model for reconstruction. It then compares the similarity among all the machines by analyzing the z-score of the same metric. In the presence of a faulty machine, the z-score is significantly higher than our predefined threshold. Minder then shapes the time window and identifies machines that consistently exhibit anomalies across consecutive windows as faulty, thereby filtering out false alarms. One important thing here is the metric prioritization. Minder calculates maximum z-score of a metric across all machines and maintains a decision tree on metric selection. Minder has been successfully deployed in ByteDance, monitoring tasks at a scale of over 1,000 machines. In our evaluation, Minder reduces detection time by 99% compared to previous manual diagnosis processes. We compared Minder with baseline outlier detection method, and it demonstrates Minder's performance by effectively detecting actual faults while maintaining a lower false alarm rate. We analyzed the breakdown of fault types and found that Minder achieves an overall precision of 90%, effectively handling CPU and GPU-related errors. From our detection results, we also discovered that models focusing on PFC, CPU, and GPU-related metrics are sufficient to address the majority of faults. So, we've so far seen how to leverage metrics to identify anomalies in large-scale training. Unfortunately, real-world bugs could be even complex, where the metrics are not enough to expose problems. Now, let's look at a different level of observability, which we found was previously missing but important: the collective communication library. Some of the most frustrating failures we see in large-scale training aren't crashes, they are gray failures. In these cases, the job slows down or even gets stuck, but none of the system metrics raise an obvious flag. Everything looks fine on the dashboard, but the iteration rate drops, and the job silently wastes compute. Such gray failure can be from a single GPU's abnormal behaviors in collective communication, which can cascade to the entire job. Here's an example that shows the blind spot. In this case, one GPU silently slowed down during an all-gather operation. Because collective communications are tightly coupled, all ranks finally get stuck. The job eventually failed when Nico timed out after 10 minutes. When engineers look at the profiler output, nothing captured. buggy information. In the end, identifying the faulty GPU required manual testing and elimination, which is pretty time-consuming. This kind of gray failure is especially dangerous because communication libraries today operate as black boxes. There's no insight into where and why communication gets stuck. Many tracing tools have been deployed across the stack to aid performance analysis and debugging. At the operation level, tools like Charka can capture execution timelines and provide coarse-grained insight into training workloads. At the kernel level, frameworks such as Nsight and npkit offer deeper instrumentation of CUDA kernel activity. However, when collective communication problem occurs, these tools fall into many limitations. First, there's a granularity mismatch. Coarse-grained tools lack the resolution to capture styles within an operation, while lower-level tools provide overwhelming details which actually mislead the debugging process. Another concern is the scalability and efficiency. Many tools are designed for offline testing, which is not suitable for runtime detection given their overhead and functionality. Lastly, most tools offer limited context for root cause analysis. They capture symptoms, but do not aid in locating the fault to a specific system or hardware component. We have seen that CCL-level information is necessary to construct the end-to-end observability and further expose important runtime information. But also we've discussed that achieving such observability at runtime is hard. Our idea is to review the dependencies, a key aspect for collective communication, and see how this can help our debugging process. We argue that we should think of the CCL as a system software, not just a library of functions. Especially for collective communications, we can think about the overall data transmission process as a global state machine. Our GPUs move through stages to transmit and sync data in different parallelisms, which involves strong control and data dependencies. We conclude these dependencies at different levels. A collective operation at a single rank depends on possibly GPU, CPU, and RDMA coordination, which involves tight control and data dependencies. Ranks in a group depend on each other for data synchronization, where downstream data transmission relies on completed upstream data coming in. Besides, operations like reduce scatter itself involves both communication and computation, which can also involve further dependencies. Let's look at an example and see how these dependencies work together at a slow all-gather operation across ranks. Nico splits data into trunks and transmits data in parallel. Since rank 0 is slower than all others, as shown in the figure, the first trunk arrives late at rank 1, which slows down the following transmission. Since it's a collective communication, all ranks are shown executing the operation slow. However, we can see that there's one single rank 0 to blame for such slowness. By identifying those dependencies, we can trace them at different levels. We first trace trunk-level information, where we monitor how data transmission is achieved along an operation's execution. This includes how much data is copied and transmitted at runtime. On different dimensions, we track flow-level information, where we observe how multiple network passes are transmitting data in parallel, which involves how many channels and QPs at the same time. Tracing those dependencies can provide further observability on how collective communication executes across our GPUs at runtime to understand what's the system state when a failure or performance problem occurs. With the idea of tracing dependencies in collective communication, we built Mycroft, a tracing system that achieves CCL-level observability and root cause analysis, again, at runtime. We instrument Nico's proxy to capture runtime information by tracking trunk movement through the communication paths, including when data is copied, transmission, and completed. Such instrumentation covers all network paths that achieve the data transmission. Mycroft generally collects two types of logs. Completion logs are generated at the end of each collective, summarizing metadata such as start and time, total data transferred, and NIC usage. State logs are emitted periodically during the operation, recording per component trunk progress, effectively producing a time-resolved view of communication behavior, especially when the latency is longer than expected. All generated logs are written to pre-allocated memory space at runtime, which significantly reduce the overhead injected to critical paths. All data collection, uploading, and further analysis are on the side of the main process. This enables Mycroft to gather runtime data at scale. Once data is collected, Mycroft is deployed in the backend to consume all those data for detection and root cause analysis. A practical question is how to quickly detect problems among a large-scale cluster. Mycroft's triggering mechanism is based on the observation that with complex parallelisms, failures or performance problems can rapidly spread across all GPUs. Our experience is that such cascading is usually within a few seconds. Given this, only monitoring a subset of GPUs is enough to implement a proactive trigger mechanism and quickly identify a new problem. We check for many types of failures or performance issues and use this to determine potential problems occurred in collective communication, where we should analyze the root cause. Once an anomaly is triggered, Mycroft runs a lightweight, dependency-driven root cause analysis. The logic varies based on the communication patterns. In ring-based operations, we compare how much data each rank has already transmitted. The rank with the least progress is often the source of the stack. We also look at the trunk-level state to determine what type of problem occurred. For example, if data was prepared but never transmitted, that likely points to a network fault. If everything was transmitted but GPU activity is stuck, that's likely a compute set issue, and we should figure out why the GPU didn't copy data. This gives operators not just a failure alert, but the direction of the deeper root causes. We implemented Mycroft as an always-on system that tracks ByteDance daily training jobs. Mycroft is a lightweight system and can be deployed on a single machine that has only 64 CPUs. At runtime, Mycroft only requires a reasonable amount of memory to monitor all large-scale training tasks in our company. Despite at this scale, the footprint on each training host is minimal. Mycroft only involves limited CPU usage and fixed 512 megabytes shared memory. This allows Mycroft to run with low overhead without affecting the training performance. From our experience, Mycroft makes no observable MFU difference for our online jobs. We also evaluate Mycroft on a testbed across a range of workloads, and we found no observable differences in end-to-end training time between runs with and without Mycroft enabled. Instead of runtime deployment, we also conducted a series of fault injection experiments to verify Mycroft's ability. We injected various types of failures into training jobs, such as slowing down RDMA NICs, stalling GPU operations, blocking the NICO proxy, or congesting the network. These faults were introduced on our testbed. The results were promising. Mycroft successfully detected all faults and correctly localized the root cause in all those cases. Here's an example. We simulated a NIC shutdown during the training. At runtime, we disabled the RDMA NIC on the GPU. Because NICO doesn't immediately crash in this case, the job just gets stuck as expected, with no clear errors in logs or other peripherals output. Mycroft quickly picked up the anomaly. It noticed that a rank stopped sending prepared data through NIC, while others are also stuck but has transmitted more data. It correctly localized the problem to the problematic GPU and identified the NIC as the potential failing component. This process was completed in just a few seconds, way before the job would have timed out. So to wrap up, large language model training demands not just the efficiency, but reliability at runtime. In this talk, we show how traditional tools fall short. They are either too high level or too heavy to help when failures silently propagate at runtime. Our solution was to effectively leverage different levels of observabilities, either utilizing the metrics or instrumenting necessary trace points to collect meaningful runtime system states. We also emphasize our argument that CCL should not be operated as a black box, and we actually can observe it in lightweight methods. We believe that bringing system-level observability closer to machine learning infrastructure will be essential as training continues to scale, or at different machine learning scenarios like inferencing, both to reduce waste and to improve robustness in production environments. We also believe that our work is just a starting point that opens the door to a broader set of techniques that can meaningfully advance long-term reliability in machine learning infrastructures. All right, by this, I want to thank you for coming to the talk.